So we have a group of equations, Newton's equations, that are used with our vertical and our horizontal components. And these are these equations are used, and we can't use, if we look at a projectile that's fired, we can't just use this and this angle. We need these vertical and horizontal components to make get more information from this vector. So there's a group of equations that we use to do that. Firstly, the vertical and horizontal part or component vectors of this vector. And we can do that, if you see, they make a triangle. I can move this one here across, and we have a triangle that's right angled. So we can use cos and sine, tan if we need it. And we can use these to help us find out some values. Okay. So here's our triangle. We have our velocity. We have our vertical component of that velocity. And I've moved it across here, uy. We have ux. Now if I do sine of theta, I get opposite over hypotenuse. Or I can rearrange that, multiply both sides by u. I get uy equals u sine theta. So this is our equation for our vertical component, our y direction, uy. We can also do the same for the ux part of our equation. So we want cos of theta equals adjacent divided by hypotenuse, which is ux over u. Cos theta equals ux over u. If I rearrange that and multiply both sides by u, I get ux equals u cos theta. So these are the two equations that I'm going to use whenever I need to find the vertical and the horizontal components of my velocities on an object that's fired. Then we can use these initial components in these equations of motion developed by Newton. Okay, so we come up with these other ones, right? So Vx squared equals ux squared. And this one, the motion in the x direction is constant. So it does make sense. We square it to get rid of any signing, but that's one of ours, and it's going to be used as an x component. We know we have an equation for velocity. Velocity equals distance on time. Distance equals velocity times time. This one, if we put our distance in, it's our x range, or our horizontal distance, equals velocity, ux, times time. The time of flight doesn't change. Sorry, the velocity doesn't change in the x direction, so it just stays as ux the whole time. So here we have another one, and that's another x. And they're the main two for the x values. We can also use the old formulas that... Oops, just get this working. Although a is 0, so you can see where that one goes. Y direction, we have Vy equals Uy plus Ayt. And that's just this formula up here. redone for the y direction. And this one's very good. It gives us often time of flight, maybe to the top of a motion, because at the top Vy is 0. The top of the motion of an object, it stops in this direction, so Vy becomes 0. Uy is often easy to calculate, and acceleration is often minus 9.8 if you're going against acceleration to begin with. Time of flight is often very important, so you need to be able to rearrange this equation to t equals v y minus uy ay. And this will give you the time of flight depending which values you put in here to the top of the arc from here to here, or for the whole flight depending which values you enter for your Vy and your Uy. I find it easier to find the time to the top in this equation and then double the time to get the time back down. We also have a couple of other equations. This one's from here, where we've added in values from the way we're looking at these graphs. This one here is the height of flight, or the maximum y direction, the range in the y direction, 2 times the gravity, usually depending whether you're going against it or with it. Here you've got your initial velocity in the y direction, and here you've got your final velocity in the y direction. And then the last one is a range, and this one's a quadratic equation, but in exams and questions often this part here disappears. If you drop an object and it falls in this direction, the y velocity is 0 usually to start with. So the object is not going down at all, it's heading this way, and then it starts to fall. And so this term here often disappears, leaving you with this part of the equation, which is usually quite easy to work out. You might have 9.8 in there. So if you worked out time, you can figure out maximum height. That's time. All right. You should try and solve a few of these problems. If you look back, there's some questions in the notes that you've got that you can help do that. If I get time, I'll do some past paper questions and give you a look at those.